these are just, we invested, more seriously, we invested $50 billion in the electrical grid and didn't increase electricity capacity by 1 kilowatt. So I cannot tell you what happened to the money. I can tell you what happened to the electricity. So I presume that this is being, corruption at gigantic scale.
Okay, join me in thanking Ricardo.
Thanks so much for inviting me and letting me share some words with you and some ideas. So unlike the last few talks, I'm not going to tell you about the collapse of any specific system. I'm going to do what Jeffrey's more interested in and tell you some toy models that give us some underlying mechanisms and insights into how things can fail. So I do study networks, and part of why I study networks is because I know that complex interdependent networks are the core of modern society. Social networks, biological networks, technological networks. And these networks are increasingly interacting with each other. They're increasingly cyber-physical. They're increasingly socio-economic. We can think, for instance, about, say, like a virus that's mutating on a biological gene regulatory network. That virus spreads over human contact networks. Those human contact networks have long-distance links enabled by critical infrastructure like airline networks. Those airline networks need all of the information and communication technology for their scheduling and for their landing. So one simple example of disease spreading that we've seen has changed radically in the last millennia. It went from local spreading to now global pandemics. And of course, things like the power grid are a socio-technical system and economic systems as well, where humans in the loop are making all of these decisions along with our automated traders. And we're seeing a lot of mismatch in timescales and ability to process information quickly. So I've been studying a lot about networks for the last 20 years from more of a theoretical perspective. And since everyone's told their origin story about SFI, I'll tell you the first time that I came to SFI was in 1996 when I was a PhD student at MIT in physics thinking about cellular automata and thermodynamics. And it's been such a great community to be part of. And many of us realized around that time that the tools we had in statistical physics were giving us some kinds of machinery that we could use to understand principles of networks. So some of the things I'm going to tell you about grew from that tradition. So we have this collection of interdependent networks with many lengths and time scales, many different kinds of heterogeneous players. And one of the challenges is that each one of those networks on its own individually is a complex system with emergent properties. So what are emergent properties? These are behaviors that are not anticipated from understanding the full details of all the equations of motion of every degree of freedom. And we have things that we see like pattern formation, like that crystal that I drew, synchronization of oscillators on networks, like our power grid, phase transitions, which is something that I study extensively that I won't talk about today, but it's when you see a radical change in the characteristics of a system, which is a small change in an external control parameter. This picture right here is looking at the emergence of large-scale connectivity in a random graph as I increase the density. But what I am going to talk to you about today is another hallmark of self-organizing systems, which is cascading failures on networks. So what I've been thinking about more than just about cascades is how are we going to control this collection of heterogeneous, multi-scale, multi-time networks. And of course, we can't just take standard ideas from control theory, which as you start from initial condition and you go to any other final point in phase space and finite time. There's beautiful engineering that discusses all of these problems for small systems, but all of these networks that I'm talking about have millions of degrees of freedom. So knowing all the degrees of freedom is not even feasible in those situations, let alone trying to control them. And of course, one of the other things is that these networks are self-organizing. So it's really exciting for us who like to do theory on self-organizing systems, but it poses more challenges. Of course, there's some opportunities that come with self-organization, and that's in the form of distributed control. But there's lots of challenges that come from self-organization, and one of the hallmarks is this cascading failures. And then the other thing is because these systems self-organize, they react in ways we don't anticipate. So I want to have a control intervention, and I do some small tweak to a system, and ends up doing exactly the opposite of what I expected. And this is particularly true when we start bringing social networks into the picture. And those human beings, they have a mind of their own, and they don't obey the math equations. So one of the easier questions is how do we model these networks to try and uncover underlying principles behind them in socio, technological, biological, all these different kinds of networks. So I was asked to speak about the end of networks, and of course, you can see from the spiel I just told you that I would be devastated if we had no more networks in the world, and obviously none of us would go home tomorrow if there were no networks. So I do want to tell you a little bit about that, though, because of course one thing about a network is that we think about collections of pairs. So a network, and just do a really simple example here, is also described by an edge list of who interacts with who. So it's a collection of pairwise dyads. And I put them all together, and I look at who interacts with who, and I make the aggregate picture, and I make that nice network that I show you there. But of course, there's much higher order interactions that we know exist. Some interactions aren't described as simple dyads. So a very simple one that everyone probably can think about is a chemical reaction. Sometimes you need three species to be present in order to have the process happen. So there's a lot of higher order things that happen in networks, and also in social networks, of course, there's a lot of learning. So I can observe the interaction between a pair of individuals and understand a lot about how I fit into the hierarchy, or I can learn what they said to one another and use that knowledge myself. Another challenge about why networks aren't going is that increasingly we're aware that these networks are what's called multiplex. So that would mean that the same set of nodes live in many different layers, where the layers are different from each other. If we think about social networks, it could be things like my Facebook friends, my work colleagues, my family members. We can think about those nodes as well as being cities, and we can think about the layers being airline networks, rail networks, road networks, etc. And another thing that makes networks more complicated is that if they're not multiplex, they're typically multi-layered. So we have things like critical infrastructure, power networks, gas networks, water networks, that interdepend on each other, and they're also co-located very frequently in order to take advantage of opportunities for economics. So for all those reasons, a network alone isn't enough of a description for the real world, but it certainly gives us a lot of insight and a great starting point. So what I'm going to talk to you about today is the collapse of networks, focusing mostly on cascading failures. So what are the mechanisms behind these cascading failures? I'm going to talk to you a little bit about self-organized criticality today, which is probably a theme that is dear to the hearts of many SFI folks. And I'm also going to talk a little bit about granting chain failures. And what I find is that repeated failure allows opportunities for renewal. And so if you have failures and repair, you need that dynamic equilibrium in order to find the sweet spot where your system functions properly. And it's this dynamic between failure and renewal that actually drives systems to this self-organized criticality, where it's a critical point, meaning that we see failures that have power law distributions of many of our sizes. And of course, since you told me, you heard me say that I'm very interested in control, I want to come up with small little interventions that can stop those cascading failures. So how did I get into this? Why am I interested in interdependence between networks and cascading failures on interdependent networks? So part of the motivation is thinking about modern electric systems. So there's certainly a massive ecosystem. So this is a map of the United States where we've got three main electric regions: the Western Interconnect, the Eastern Interconnect, and Texas. But of course, we can also break this down into smaller granules as well. So in each one of those regions, there's a whole ecosystem of energy providers. So the big steam turbines, some of those are owned by municipalities and they're non-for-profit. Some of them are owned by big corporations. And now we see the advent of renewables. So we've got wind and solar, and these are highly distributed sources. And typically they are in locations far from where the population density is. So our wind farms and our solar farms are typically geographically distant from where the demand is. So we're building a lot of transmission lines to accommodate this. So the lines shown here in yellow, orange, are all new lines that are planned in order to help distribute the flow of energy that we make. And one of the questions that we wanted to ask is, does that increasingly distributed nature stabilize or destabilize the system to cascading failures? And one thing I do want to mention, of course, is that these black ads cascade from one grid to another. So if you have a failure within your own power grid and you only affect your customers, you're fine. If your failure cascades to another grid and cascades to another grid and ends up causing a massive outage, suddenly you're facing $1 million fines by FERC, the Federal Energy Regulatory Commission. So there's a lot of challenges and monetary reasons why you don't want cascading failures. But one of the most important challenges is that we can't store power. So we don't have good ability to store power. And we need the supply and demand to always be matched. So it's really fascinating. If you look at energy markets, energy trading markets, they'll often have negative pricing. So what is a negative price in an auction? That means someone's going to pay you to take this good. So it is such a challenge to balance supply and demand that if you've overproduced and you don't have enough consumers, that power has to go someplace. And you hope that someone will take it. And if no one wants to buy it from you, you want to incentivize them and you say, please take it, I'll give you money. And if they won't take it, then finally you have to dump all of those electrons into like a big resistor grid that you made that dissipates and causes damage to your capital. So definitely things that we want to avoid. And so we're talking about the end. I did want to just mention that if we could have batteries that actually work, we would have the end of the renewable energy integration crisis. So if you talk to any power grid operator, it's really fascinating because, of course, this is the biggest challenge that they're facing, is the volatility of wind and solar and the fact that those big steam turbines were never meant to be power cycles. You're supposed to turn that steam turbine on and leave it on for years. And now the power grid operators are finding that in the middle of the day, when there's plenty of sun, that they have to ramp down that big steam turbine generator. So there's a lot of challenges that are facing us because we don't have good battery technology. So that's aside from the network, but it certainly is an end that I wanted to mention. So how are we going to model cascading failures from a simple idea? And for this, we turn to an idea that was introduced in 1987 in the physics literature by Boxing and Weisenfeld, thinking about self-organized criticality and sand plant models. So we're going to think about grains of sand that are falling uniformly at random on a network, and those grains of sand represent some kind of load. So load arrives, and it has to get processed by the node at which it arrives on. And we're going to say that every node in this network has some capacity to store sand, and for simplicity, I'm going to make that capacity equal to its degree, its number of neighbors that it has. And as soon as the grain of sand falls on a node that would reach its capacity, that node is going to shed a grain of sand to each one of its connected neighbors. So for instance, if the grain fell on this node right now, it would be at capacity having 4 grains of sand at degree 4, so it would shed 1 grain to each one of its neighbors. And you'll see